Welcome back. Today I want to explore this fundamental theorem of calculus in this particular form. You'll remember this is the relationship when we divide after we multiply. So what we have here is a multiplication in disguise. We're simply multiplying small amounts of height times a smaller change in radius, and then we're adding them up in this big sum. Then we're looking at the overall rate of change, the derivative. It comes back to the formula division of multiplication is the reciprocal. This is simply a glorified form of this formula, up to approximations, using this limit method. The fact that these two are reciprocal of each other comes down to the basic fact that multiplication and division are designed to be reciprocals of each other. The results of the fundamental theorem of calculus guarantee that this result would be the value on the inside at that value r. That is, it's changing at exactly the rate of the inside value. Now, the goal of today's lecture is to strengthen that understanding, and I have these nesting dolls to help me with that. The concept of nesting dolls is that you can take each apart and fit one inside, and you stack them inside, and eventually they become one solid unit. But inside, they're built on these smaller pieces. The overall perimeter is the same at each time. We just have a tiny thickness, and we add them up over time. This is known as the method of shells. The result is that the volume of this final grandmother is the same as the sum of these thin shells. If this isn't precise enough for you, you can always ask for thinner shells. You'll have more grandmothers, they'll still add up to the same total volume, which is the point of this exercise. This sum here is what we see here. Now, what does this have to do with the rate of change at r? Since we can always subdivide the thickness to be thinner and thinner, we can always imagine that that thickness is so thin that we're not really counting it towards any of our calculations. It's well below the margin of error that we're interested in seeing. When the thickness becomes very thin, that is, below the margin of errors of anybody's count, we can start to say that most of the volume is coming from the total shell's boundary, the perimeter. That is, the surface area of this. So if we look back at our formula, the thing that's counting towards our surface area is just the y of r. The thickness dr becomes negligible as we get better and better approximations. So in a sense, it's as if we're summing up a bunch of paper-thin perimeters and getting a total volume. And of course that makes sense. After all, you've held onto a book. A really thick book is the sum of tiny thin pages. But if individually we're trying to say why this weighs so much, we wouldn't necessarily think that the weight of the paper varies that much because of its thickness. It's mostly because of the size of the paper, the surface area. It's very difficult to measure the thickness of any one page, but the result over time can accumulate. So in the same way, the sum of these different surface areas are all we need to worry about to get the total volume of the system. That's what the fundamental theorem of calculus guarantees for us. It says that at some level of precision, you get the thickness so thin that no one can dispute the fact that that's not contributing to the total volume. If we make that thickness dr so small, then it won't contribute to the total measurements of the volume. It'll actually be just whatever the values of the surface area are, up to rounding errors. At that point, we can say that we're adding up a bunch of surface areas. It's not quite precise and you know it, because surface areas, for example, would be measured in things like meters squared, and we need to get to meters cubed. That little thickness is providing us with a change in units, for example, so it's absolutely necessary that it be there. And it does contribute a tiny amount of percentage change, but that is simply within the margin of error that we're discounting, and therefore it doesn't change the value of this, just the units. So if we think of the change of the volume as a rate of the radius, we claim that that is going to be the same as the surface area at any one particular point. That's what's being expressed in this formula, and that's the method of shells. But of course, it's difficult to measure the surface area of this nesting doll, and it's hard to measure its volume as well. So perhaps we should start with shapes that we trust, like squares and circles. That's how you take care of half a chalkboard. The two measurements I might make of a box would be the boundary and the hole. Now, in our traditional telling, we do length times width, so we assign these both values. Let's assume this is perfect square. Since this is a rectangle, we know that its boundary is simply to add up the sides, x plus x plus x 4 times. Likewise, the hole is the multiplication of the length of width, x squared. Now, what I'd like to do is try to relate this to the relationship of boundary and hole for other shapes that are similar to it. For example, a line segment, or a cube. Here, the hole is the entire length. It has length x. For the boundary, we have to think a bit harder. We can see that the boundary are the two endpoints. I'll call that 2 for those 2 points. The boundary of a cube would be the surface area, and if you think of a regular dice, you'd see that there are 6 sides to the dice, and there are 6 faces to this cube. Therefore, we have 6 of those times the area of each one, which is x squared, 6x squared. Likewise, the volume of this cube is known as x cubed. Now, if we look for patterns between these, we might get lucky and guess what the pattern is, but we'd like it to be systematic. But let's take this fundamental theorem of calculus seriously. If we see this rate of change, we should be able to say that the derivative, the rate of change of the total volume, should therefore be this value inside, which is our y of t. Let's see if we can rewrite our structures in a way that would let us see what these two numbers are. Having visited the method of shells, we now see that there is a justification for thinking of a relationship between the boundary of a shape and the volume of it takes in. However, that was based on starting in the center and expanding out with a radius. So let's reparameterize everything we have here using a radius number. I've simply replaced my x's with 2r, where r now is the radius of this particular square, line segment, or cube. It's the measurement from the center to the closest boundary. Once we have this notion of radius, we can start to reparameterize our storyline. Standing back to see this in terms of radius, we can now draw a stronger conclusion, one that is justified by the fundamental theorem of calculus. First of all, the rate of change of a line of slope 2 is 2. Our first fact about the derivative is that the derivative of 2r is equal to 2. It's a line of slope 2, it changes at a rate of 2. This next one says that 4r squared needs to become 8r. As a quick check, we should see that the units would match up. This should make sense. After all, the derivative is getting us closer to the perimeter of the structure. So if the value is measured in meters squared, then the output should be measured in meters. If the value is measured in feet squared, then the output should be measured in feet. Finally, 8r cubed should turn into 24r squared. If you think ahead, you might be able to think of a general formula based on the fact that an n cube has a predictable volume and perimeter. The result is going to be that we take 2r n times over to get its volume. That is, 2r raised to the n will be the total product of all those sides. The instructions to fathom an n-dimensional cube are as follows. Every time we seem to double something, we took this line, we doubled it to make a square. Then we took the square and we doubled it to make a cube. Each time we connected all the points that we had before with vertical lines and all the faces with vertical shapes, so forth. So if we wanted to double the cube, we'd have a cube on the top, a cube on the bottom. On each of those faces, we include other cubes, 6 new cubes. And we add to that 2 more. Therefore, we end up with n times 2n minus 1, rn minus 1 of those values. Therefore, we have a geometric reason to believe in both of these formulas. This is the formula of the boundary of an n cubed, and this is the formula of the volume, the whole of the n cubed. And so we get a formula for the derivative of these two values. One final bit of trickery. If we imagine what's happening with rates of change, every time we multiply by some number, we simply multiply the rate of change by that exact number. Likewise, if I multiply by 2 to the n, I'm able to do it before or after I take the derivative of r to the n. In particular, I can drop it from my formula. Altogether, we get a very valuable tool that tells us how to do the derivatives of r powers. Once more, let's do a quick concept check. If this was a cube, we could be thinking about cubic meters. When we're done measuring the boundary of a cubic meter shape, a volume, it should be measured in meters squared. So the number should come down by 1. This conceptually matches up. The fact that n is the right multiplier is a consequence of the arithmetic. We can see that we're forced to choose n as the multiplier whenever we try to balance what the rate of change is in this formula. We simply write down the values that we can see directly from the geometry, and we solve for the missing growth. In this case, it's by n. There are other ways to prove this, entirely algebraic methods, and it shouldn't surprise you. After all, the reason we know the area, volume, and so forth of these rectangular shapes is because we define them to be the multiplication. It's the fact that integral systems are the sum of their parts, and likewise, the distributive law in multiplication lets us capture that algebraically. So the fact that algebra captures the exact same formula as the geometry should be no surprise. Similar to how we worked out with squares, we could work this out with rounded shapes like circles. Now here you're going to have to trust me on some of the formulas for what the surface area and areas and volumes are of these different shapes. They're not easy to memorize, but many of you will already know these, and this is just meant to reinforce our understanding of the fundamental theorem of calculus. The goal here isn't to prove everything, it's simply to make you feel like the fundamental theorem of calculus seems natural and valid. You've seen it already. You believed it already if you believe these numbers. Let's take a look at the boundary of our simple line. We already saw there's 2 points, so the boundary is 2. The whole in this case is 2r. For the circle, I'm just going to ask you to believe me that when we take the ratio of the circumference divided by the radius, we get a constant. That constant is 2 pi. We call that the circumference of the unit circle. There's a lot of reasons for why you might be able to prove that to yourselves, but I think at this point you're comfortable with that concept, and I'll take it as a gospel. What I want to then do is predict what should happen to the whole. The whole should be to add up 2 pi r several times. How many times? Well, if we think of a bunch of concentric circles from 0 up to capital R, then there will be how many of them? Capital R of them. So we would think that it has something to do with r times our circumference of 2 pi r. However, this isn't quite right. If you know the area of a circle, it's pi r squared, not 2 pi r squared. But this actually makes some sense. pi r squared is changing at some rate, and that change in rate has to be the circumference. But this should make some sense. The inside circles are changing at a faster rate than the outside circles. If we keep dilating, we keep adding smaller and smaller amounts around the boundary. So we start to see the relationship that we saw with the square. If I take the derivative of the line of slope 2, I get 2. And if I take the derivative of pi r squared, the constant doesn't matter, but the r squared becomes 2r to the 1. That was the formula we saw before. That is, the derivative gives us the circumference. Likewise, when we go to the sphere, we see a similar relationship. Once more, I'm going to ask you to trust me on what the surface area of a sphere is, but I'll give you some justification. The surface area of a sphere of radius r is known as 4 pi r squared, and you can just about see that when you hold onto a tennis ball or a baseball. When you hold onto a tennis ball or baseball, you'll see that there are laces or grooves inside of this. And if you track the grooves, it looks like a giant S shape on one side, curving onto the backside. You'll carve out 4 specific patches, and that's because the first patch is approximating one of these 4 circles, and then one behind it is with the second one. The 2 on the sides are the other 2. Now, it's only an approximation. You can't smash 4 circles onto the sphere in a nice way, but this is the closest representation that you can have in everyday living to remind you of the actual formula. Once you believe that formula, you can make a prediction about the volume. The volume should be something that changes at a rate of change equal to this value. Let's see if we can guess what that might be. The volume formula is going to involve something with cubes, something like an r cubed. When we take a derivative of an r cubed, we know that we have to lower the units to an r squared. That'll compensate for this. But there's an extra piece of this. We also have a 3. The 3 will come down in front. That was from the algebra of the rules. So we'll end up with 3r squared. But over here we have 4 pi, not 3. So we have to compensate. We can put 4 pi in front of here and then divide by the 3. And indeed, that is the exact volume of a sphere of radius r, 4/3 pi r cubed. This pattern continues on at any scales. For example, the known volume of a hypersphere in 4 dimensions is, and its surface volume is. Once more, when we take derivatives, we recover the same formulas. The fundamental theorem of calculus in this form is telling us that the rate of change of growing something by putting thin shells on the outside is dominated by the surface area of the thin shell. And this makes logical sense. We're adding such a tiny thin layer that the total value of the volume that's added is dominated by the outside surface area. The thickness is still required. After all, we have to change the units from, say, meters squared to meters cubed. But it's just that that thickness is so small that it's within any margin of error as contributing to the total volume. So in terms of the approximations we're after, that is, in terms of the limits we're after, we can just set that thickness to be conceptually equal to 0, because what we'll actually do is always make it so small that you won't even notice it in the accuracy that you're willing to check. The results are that things that we've measured classically by other methods should start to reinforce your belief in the fundamental theorem of calculus, that the rate of change of pi r squared, the area of a circle, is the same as the circumference of the circle, is a key observation that you could have made at any point after you learned about these concepts. Now you can observe them as part of the fundamental theorem of calculus and put them alongside a lot of other things. This is just a demonstration that knowing part of a story together with the fundamental theorem of calculus lets you solve for missing parts. Until next time. That's how you take care of your chalkboard.